Test. Test. Why is it always so low? Hello? Alright. Let's just get into it. So 2.2 is about the geometry of systems. In 2.1, we displayed R and F graphs of solutions to two different predator-prey systems, but we did not describe how we generated these graphs. We will ultimately answer this question in 2.5, in which we generalize Euler's method to produce numerical approximations to solutions. We must begin the explanation by introducing some vector notation. This notation provides a convenient shorthand for writing systems of differential equations, but it's important for a more fundamental reason. Using vectors, we build a geometric representation of a system of differential equations. As we saw when we used the slope fields in Chapter 1, having a geometric representation of a differential equation gives us a convenient way to understand its solutions. All right, so the predator-prey vector. So we have a predator-prey model. We can plot the graphs of R and of t and f of t as functions of t, or we could plot the solution curve RT, FT in the RF plane. We can think of this as a combination of the two scalar value functions. There are advantages if we take this approach. Vector valued function in the RF plane. So this is the definition of a vector field, or a vector value function. To compute the derivative of the vector valued function p of t, we compute derivatives of each component. Okay, this is just rewriting the system. We've converted our first order system consisting of two scalar equations into a single vector equation involving vectors of two components. The advantages of the vector notation start to become evident once we consider the right-hand side of this system as a vector field. The right-hand side of the predator-prey system is a function that assigns a vector to each point in the RF plane. If we denote this function using the vector v, we have v for example, at the point RF equal to 2, 1. Okay, we're just evaluating the function. Okay. To save paper, we'll sometimes write them as rows or columns. V can be evaluated at any point in the RF plane. The use of vectors enables us to simplify our notation. Okay. The vector notation is much more than just a way to save ink. It also gives us a new way to think about and visualize systems. We can sketch the vector field V by attaching the vector V of P to the corresponding point P in the plane. Okay, that's computing V of P for many different values of P and carefully sketching these vectors in the plane is tedious work for a human, but is the sort of job that computers and calculators are good at. A few vectors in the predator-prey are in figure 2.17. In general, we visualize this vector field as a field of arrows. The vector field for a simple harmonic oscillator. I feel like I have a hard time wrapping my mind around the harmonic oscillator. Okay, if we just like try to solve this thing. See, we're gonna see how well this does. But okay, so what was this? I mean, the general form of these is And then you can rewrite this as, how's my volume? Is that okay? So, um, so then what we have is, but how do you actually solve it? I mean, you can just like recognize that the second derivative, that y double prime is equal to minus y, is an oscillatory function, but how do you really solve it? Okay, they just introduced this thing called the direction field. Well, the direction field gives a picture that is much easier to visualize than the vector field. There's loss of information, okay. In general, for a system of two variables, this is the form. This is an autonomous system, too. Okay, so let's think about this simple example. So you're going to have e to the t here, right? And you're going to have e to the y here. So what does that look like? Let's just look at that. So if we have then if we're here, we should just go, and if we're here, we should go here. We're here, we should go here. So it's just going to be, but if, let's say if y is negative, I think if y is negative, so wait, let's just do this. Wait, but what does that mean? If we're at like if x0, y0 is at 1 minus 1, then this is equal to 1. And no, I think it is. I think it just goes. Yeah, it just goes away. Because if it's negative, it becomes more negative, right? Okay. So it's not like it decays. There's no decay at all in this scenario. But this one decays all the time. Yeah. We can think of the picture of a vector field or a direction field as a picture of a system of differential equations. We can use this picture to sketch solution curves of a system. To be more precise, let's consider the general form. As we've seen, this system yields. So when we say y, right, y is just the state vector, right? Right. We can think of the picture as a vector field or a direction field as a picture. Interpreting this vector equation geometrically is the key to a geometric understanding of this system of differential equations. If we think of a solution as a parametrized curve, dy dt yields tangent vectors of the curve. To help visualize solution curves for a system, we can imagine an infinite, perfectly flat parking lot. Okay, that's a hilarious metaphor. Okay, a solution curve of the harmonic oscillator. For example, in 2.1, we saw that the functions cos and minus sine satisfy the harmonic oscillator system solution. In figure 2.27, we see that the relationship between the solution curve and the vectors in the vector field. Oh, okay. Just as there are special points equilibrium points on the phase line. There are distinguished points in the phase plane of systems of the form. Oh, wow. Okay. These points correspond to constant solutions. Y0 is an equilibrium point for the system. If f of y0 is equal to 0. The constant function is an equilibrium. Okay. Equilibrium points are simply points at which the right-hand side vanishes. If y of 0 is an equilibrium point, then the constant function is a solution to the system. Notice the, yeah, exactly. Okay, finding equilibrium points. Okay, so a simple like linear system like this amounts to literally just solving the linear system of equations. So 0, 0. Oh, right, yeah. There's this whole thing about finding the eigenvectors to figure out what this line is on which it grows in a straight line. What's up, Raman? All right. If we look at the vector field for this system, we see that vectors near the origin are relatively short. The solution curves move slowly as they pass near the origin and faster when they move away. But I guess what I want to know about this is like, I'm pretty sure it's like if we have x dot equals a times x vec a matrix, then solution is x of t is equal to x c times x a t, right? Oh, okay. The matrix exponential I've seen so many times. It's still so weird to me. Matrix exponential is crazy. Okay, so these are the solutions. So we're going to get to that after. All right. But the point is, what am I trying to say? Well, I mean, this gives us an explicit function for the solutions. But the eigenvectors of A tell us which solutions move exactly on straight lines, right? If V is a real eigenvector of A, so if your initial condition So if your initial condition is on one of the eigenvectors of A, so this either basically yeah, so if lambda is negative, then it decays, and if it's positive, then it only real eigenvectors give literal straight line solutions in Rn. Complex conjugate eigen I don't know about that. Okay, anyways, it's more advanced than we're actually going into, but I was just curious. Okay. If we look at the vector field, we can see that the vectors near the origin are relatively short. Thus, solution curves move slowly as they pass through the origin, near the origin. We can, oh, interesting. We can still tell that there must be an equilibrium point at the origin because the directions of the vectors in the direction field change radically near the origin. As a solution passes near an equilibrium point, both x dot and y dot are close to zero. Therefore, the x of t and y of t graphs are nearly flat. It doesn't have to be that they're near zero, but they do need to be flat. As the solution curve travels near an equilibrium point, the x of t and y of t graphs are nearly okay. A population model for two competing species. Include within an analysis of the system. Give one more cup of coffee. Okay. To illustrate all the concepts we introduced in this, we conclude with an analysis of the system. X dot equals 2x. We think of x and y as representing the populations of two species that compete for the same resource. Note that left on its own, each species evolves according to a logistic population growth model. So if y is 0, then dy is 0. So, anyways, it amounts to finding the equilibrium solutions. The interaction of the two species modeled by the xy, for example, effect. Okay, let's just write this system and try to solve the equilibrium on our own. All right, so what is the system? We have x dot equals 2x 1 minus x over 2 minus xy, and y dot equals 3y 1 minus y over 3. Okay. So first off, x0, y0. What would we write here? We would say y, big Y of t. But just say u. U will be our designated vector. U of t equal to 0, 0 is okay. So now we need 2 minus x minus y equal to 0 and 3 minus x minus y equal to 0. So we could turn this into a linear system of equations. So we get x plus, wait. This needs to have a 2. There we go. So it's going to be 2 minus x minus y. And this is going to be 3 minus y minus 2x. So we get x plus y equals 2. And 2x plus y equals 3. This is the system 1, 1, 2, 1, 2, 3. So the simplest way is probably just substitute. So x is equal to 2 minus y. So then we get y equals 1 because 4 minus y equals 3. And then x is equal to 1. Let's see. If x equals 1, we get 1 minus 1 equals 0. And then we get 3 minus 1 minus 2 equals 0. Okay, so then we have 1, 1 is another. Okay. And then finally, but see, this is my problem. It's like, you can grind through this, but how do you know that there's another one? So, like, because I know that. Okay, so, like, so let's just say if we have a quadratic and a quadratic, like, let's just do, then this could have 2 solutions and this could have 2 solutions, right? So there's probably 4 solutions. So if x equals 0, yeah, so, okay, so yeah, let's start with take y to be 0. Then we have x times 2 minus x equals 0. X equals 0 or 2. Then we have, if x equals 0, we get 3 minus y. Y times gives. Wait, but this doesn't, yeah. So this is going to be, so we have 0, 2, or wait, 2, 0, and 0, 3. Okay, so that's that problem. That's a pretty basic problem, though. But I don't know, it takes me so long. All right, I'll be right back. All right. Okay, so we just did that. Sketching the phase portrait. So how do we determine if it's um uh in one dependent variable we get that linearization about a point tells us the stability. How do we do it for systems? Okay, and let's get into this. Okay, so this is going to be yes, this is going to be 2x as how do I take the Jacobian? I think it might just be D, right? I think you just use D. D of f of x, y, x of t, y of t. That didn't work out. Okay, wait, let me read this first. You compute the Jacobian. You evaluate at the equilibrium. So wait, so wait, what? Form the linearized. Oh, that's so fucking cool, man. Does this work? This works for nonlinear systems too, right? This is so sick. So I don't really get this. Form the linearized system. Yeah, so if all of the eigenvalues, then to first order y dot if any, that's what's crazy is if any, dude, that's what's so cool about the systems, man. If any are eigenvalues, any eigenvalues, right? If all no, here's an example. Wow, this is advanced. I don't know that theorem. Okay. This Jacobian is going to be 1 minus, yeah, because this goes to 0. And then this is going to be, right, this is going to be df1 dx2. So minus 1 minus x1. Okay, so we know how to compute the Jacobian. Oh, is that r mean the real component of that? So you find the equilibria. Then you linearize about an equilibrium. So, wait, what? I don't really get that. So this is the Jacobian at 1, 1. So it's stable from this point, kind of. Yeah, okay, so it's a saddle. I get it. It's a saddle. That makes sense. Because, like, you can go along this trajectory or this trajectory and you'll land there. But then if you get kicked, so if you actually get kicked in exactly those directions, then you'll come back. But if you get kicked at all in the other direction, so this means that it's unstable. Hmm. So there is a test. So you don't actually have to, right? Because really, you just this is cool. Yeah. You know, they really ought to have more. I mean, they almost never say the time complexity. It's like I don't know. Anyways, okay, so that's interesting. All right, I'm glad we did that. Okay, should we work through an example then, just to really think about it? Okay, so what? Okay, so what is the process? The process is find the equilibria. All right, so let's do a 1D and then we'll do a 2D. I don't know. Let's pick like something like that. So we have the phase line. Okay, so then so if we have 10. Okay, so this is less than 0. Um, so we have 0. We have 10. This is 10. This is 0. So this should look like a. So wait, 0 is positive. So 0 is. So it's gonna look like this. So therefore, this is sync. And this is a source. Okay. Are we getting everything? Yeah, we are. All right, let's do a 2D example then. So what did we have? We had the equilibria. Okay, we want to find one's stability. Okay, so J. So we're gonna have. Wait, actually, let's make this. Okay, so partial f1 partial x is equal to 2, right? Okay, and then this one is going to be 0, 0, minus 1. And this one is going to be, with respect to x, is going to be minus 2, 2y. Oh, and this one's going to be minus x. And then this one is going to be 3 minus, this is a 2, right? And this one is going to be, okay. All right, so that's the Jacobian. So now we want to evaluate the Jacobian at 1, 1, right? So j of 1, 1 should be 2 minus 2 minus 1. This is going to be minus 1. It's going to be minus 2. It's going to be 3 minus 2 minus, wait, is that right? I think that's right. Okay, so that's the Jacobian at 1, 1. So this is the analog of like f prime of x, right? But oh wait, actually we should write it like this. So we have 1, 1 right here. This is 1, 1. And we know it's a saddle, so we know we have like a line here, and we have a line here. Then we also have lines here, and here. This is 2, 0, right? And this is 0, 3, and this is 0, 0. So how do we find out? I know it's take the determinant of this characteristic. So it's like that Jacobian is A, and then you're gonna do like A is equal to A minus lambda I, and then you compute the determinant of that. So then you get minus 1 minus lambda. Oh wow, you can't see that. Okay, you get minus 1 minus lambda minus 1 minus 2 minus 1 minus lambda. Okay, and then the det of this is AD minus BC. So we get it's gonna be 1 plus 2 lambda, right? Plus lambda squared. Wait, it's gonna be let me get a notebook just so I can like write some stuff down. Okay, so wait. Okay, yeah. So that is correct. So but then we get the minus 2. So we get lambda squared minus 2 lambda, or plus 2 lambda. Oh, you won't be able to see that. Alright, so let's get rid of all this. So the determinant, or the characteristic polynomial is lambda squared plus 2 lambda minus 1. Right? Let me double check. Okay, yeah, that's correct. Equal to 0. So you're solving that. And so basically you're finding the values. You're finding the values of a minus lambda I. So you're finding equal to 0. So lambda minus 1 plus or minus square root 2. Okay. And since one of those is positive and one of those is negative, it's unstable, because if any of them are positive, then it's going to explode. All right, so that's like a simple linearization. I think I get it. Not that I'm ever going to have to do this on this quiz, but I do kind of like knowing that I could check the stability if I needed to. Okay. The phase portrait is just one way of visualizing the solutions. All right, so you can plot it over time as two separate ones. This I didn't understand. In the phase plane, we also note that the solution curve for the initial condition crosses the line y equals x. Oh, okay. So you can find when the populations are equal. In all the systems so far, the independent variable has not appeared. As we said in 1.6, systems with this property are autonomous, self-governing. An important geometric consequence is that the vector field only depends on the dependent variables and not explicitly on the value of the independent variable. Therefore, we do not need to consider it. Okay, cool. We're on to the problems. All right. All right. Okay, we do probably want practice with this. So we're going to do 1, 3, and 5. All right. Do 1, 3, and 5. I'll write them on the board. How clear is this? I feel like maybe I should improve the lighting. Maybe that's a little bit better. Okay. So this was stability of a equilibrium point, stability of a fixed point for a system. I don't know enough linear algebra to understand those eigenvector things, though. All right. Okay. Determine the vector field. Make a rough sketch of the phase portrait. What exactly is the phase portrait? Oh, the phase portrait. Okay. And then, so we're going to skip C and do phase portrait. Okay, so problem 1 is x dot equals 1, y dot equals 0. So this one is just going to be so first off, vector field. So this is A. B is we're going to have things going this way, and this way, and this way. Basically, no matter what, it's just going to be going that way. Okay, so that one's easy. So basically, to put it in words, no matter what, it grows. Hey, get the chair out of here, man. Okay, problem 3 is okay, so what does this mean? This means that dy dt is equal to minus v and dv dt is equal to y. Yeah, so this is a solution. So then I think we're gonna have so the wait, but we need to figure out which direction it's moving. So at f of 1, 0, we're gonna get 1, 0. So that means that wait. No, this is wrong. So at 1, 0, we're gonna get um 0, 1. Yeah, so this is pointing up. So we have a clockwise. Or counterclockwise. Counter. So this is V and this is Y. So when Y is high, dV is high. And then when it's low, dV. And then similarly here and here. Okay, great. So it's tangent at the thing. Okay, 5. 5 is the opposite. 5 is just so you just get a circle going this, this way. Clockwise. Okay, so that's that. Okay, 7. Oh wait, we can 7. Convert the second order differential equation into a first. 7. Is that even visible? Can you even read that? Probably can't even read that. But this is going to be y prime minus y. So if we're at 1, 0, it's going to equal to 0, 1. So wait. Did I do this wrong the other time? In 3, we had I think I did 3 wrong because I didn't actually. If you have 0, 1 here, then you're gonna get minus. Or f of minus 1, 0. Goodness, minus. Okay, so I think that this is right. But then this one, this is like this, but then f of okay, so I think that it goes like this. So we have like a. So then if we have like f of minus 1, minus 1. So I think that these come in like that, right? Right, so it's something like that. So basically, but if you're at like 5 minus 1, then so then y is decaying and v. Yeah, okay, so this is right. Okay. All right, I think that that's it. So basically, if you're in the first or third quadrant, then it blows up. And if you're here, you know what we should do? Let's do our freaking Jacobian. This is going to be fast. All right, so our fixed point is 0, 0. So equilibrium is 0, 0. Then what we want is J is equal to, so we have 1, 0. So the Jacobian is the identity, which is cool. So, so what are we trying to do? We're trying to do, so we're going to get 1 minus lambda, 1 minus lambda equal to 0. So then we get 1 minus 2 lambda, lambda squared is equal to 0. For the determinant, det So isn't this equal? So this is, I mean, this is 1 minus lambda squared. What am I talking about? So then lambda must be 1, right? Wait, but there's a second. Let's try to do this on a computer. Okay. X dot, or let's do y dot equals v dot equals y. I want to do stability analysis on the 0.00. Yeah, I feel like I messed something up. Oh wait. No, you know what? I got it wrong. I got it wrong. Because yeah, so wait, hold on. I knew the Jacobian looked sus. This is not right. The Jacobian is 0, 1, 1, 0. So we're gonna get minus lambda 1, 1 minus lambda. Det of this is equal to lambda squared minus 1. So then we get lambda equals plus or minus 1. So basically, if you go on this way, and I'm sure we could find, so I shouldn't have drawn that. But I'm saying if you get nudged along that axis, I think you come back. Or actually, I think if you get nudged along anywhere here, let me see. So, so it's a saddle point. Does this mean that if our initial condition is in the second and fourth quad, then we decay to the equilibrium point. But if we, because I don't know if that's actually true. I think. All right, let's plot the Oh, I don't think that's right. What? That's not right. Because if we're here, wait, what? If you're at 1 minus 1, or minus 1 goes to minus 1. So if you're right here, then you are going to go up and over. This doesn't even look right. Wait, this is like definitely wrong, right? Oh wait, you know what? I'm silly. There we go. Okay, so I don't think. Wait, actually, you know what? No, it's actually not even that. You can cross the 0. So like, you're gonna go like this. Okay, so wait. So it's not that if you're in that second quadrant, you go. You have to be directly on the. You have to be directly on the eigenvector. Okay. All right. So we're gonna move on to problem 9 now. Okay. So I've always want to ask this though. So in a system with noise, basically all unstable fixed points basically disappear. Kramer's escape? Huh. Anyways, all right, it's problem 9. Let's just keep hammering these problems because I have a lot to do. Okay, so all right, I don't know if we're gonna do this one on the board. You know what I don't understand? Actually, we are gonna do this one on the board because number 9 is kind of weird. Okay, so no matter what along y, you're decaying, right? So you know you're gonna be decaying no matter what. But along x. Anyways, the trajectories are kind of like this. So you're kind of stretched along this line. But the thing about that is, B, describe behavior of okay, so the thing about that is or Holy shit, I feel like I actually understand the geometry of eigenvectors. Okay, so this is so cool, actually. So you're trying to find... Yeah, you're basically trying to find the vector that you can cause to squish things down. Very interesting. That's so cool. Yeah, right. Because so okay, so wait, so A was basically this identity thing, and since there was a 0 here, so wait, what if we did like... Hmm. So in that case, okay, all right. This isn't linear algebra class. Let's keep going. But that is really interesting. Eigenvectors are so sick. Okay. So anyways, what we did for number 9 is you solve for what? So your goal is to find the values of lambda that cause A to be singular. And then you solve for A minus lambda. Then you solve for A minus lambda I times your vector is equal to 0. So then you solve this homogeneous equation and you get your eigenvectors. Okay. So 1, 0 is unstable, and minus 1, 1 is stable. Okay. Very interesting. Very, very interesting. All right. Number 11. Oh, this one. Okay. All right. Let's do this one. This one's fine. So, so this one we can see we have 1, 0 looks like a saddle, and this is a little confusing. Why is this like that? What's up with that? That looks goofy. I think that's because is there really one pointing that way? I don't think so. But anyways, okay. So we have a stable at minus 1, 0, and we have and a saddle at 1, 0. Oh my god, this thing is so annoying. Okay, so x squared minus 1. Okay, so I'm gonna double check my answer. I think I already did this problem, but I'm gonna do it again. So for 11, we have... It could also be this one, but the reason why we know it's not this one is that if we were at like x equal to 0, y equal to 1, we would see it going up. And similarly, if we were at x equal to 1, dx would be 0, but y would be, and if y was anything, it would start growing away. But the arrows point in. So I'm going to say that a goes to 7. Because if it's minus 1 here, let's say it's like we're at like 1/2 or minus 1/2 is 0. If we linearize, we get 2x, which is, yeah, okay. So so it's stable at minus 1, so that's good. Okay, b goes to, so b is one of those ones that's going to be like, okay, it's kind of like the reverse of this one. So it's probably something like, okay, so x just decays. So dx is probably just going to be like x. So it's probably going to be like this. But it can't be this one. Oh, wait. It actually doesn't have to just be that. But let's see. What we do know is that universally y is decaying. So it's got to be 8, 6, 3. Okay, so we've narrowed it down to 3, 6, and 8. Now, a fixed point here would be 0, 1. Or 1, 0. But 1, 0 doesn't look to be fixed. So it's not 6. Now, if I kind of want to just linearize both 3 and 8 just to get an idea. So we're going to have, or not linearize, but we're going to have 1, 2, 0, minus 1, and we're going to have 1, minus 2, 0, minus 1. So these are the two that we're comparing against. And we're going to have 1 minus lambda times minus 1 minus lambda for the first one. And then the second one is going to be, so the eigenvalues are going to be the same, but the eigenvectors are going to be different because we're going to have, so wait, hold on, we're going to have minus 1 minus lambda plus lambda minus plus lambda squared. So we're going to have lambda is equal to plus or minus 1 for both cases. So then we're going to have 1, 2, 0, minus 1, minus 1, 1, 2. This will be 0, 2, minus 2. So we're going to have the second column is 2 minus 2 in the first case. But how does that tell us what the eigenvectors are? Because we need to solve this equal to 0. It's going to be, how did they know that an eigenvector is... Wait, we seek v1, v2. Okay, we just want to find, so we need to find non-zero vector for a minus lambda I v equal to 0. Okay, so if we take x equal to 1, y equal to 0, then we get 1 minus 0, or wait, no, 0 minus 0, 0, or 0 plus 0, 0 minus 0. So 1, 0. Okay, so in our case, we got the same thing. So 1, 0 is an great. So, but for the other case, we have the same thing, right? So if we take so a is equal to 1, 2, 0 minus 1. Wait, what? So that's minus an x plus an y. So that's like on this line. And then 1, 0. Okay, see, that's what we need. We need to plot those eigenvectors. Because if you plot those eigenvectors, you get the boundaries for where trajectories start to change. Oh yeah, wait. Oh wait. So we never calculated the other one. So the other one is 2, 2. Oh, okay. So then x equal to minus y. Oh, okay. So for this has got to be this one, because trajectories shift along the x equals y line. So I'm going to say that b goes to 8. Okay, now c blows up in y faster than x, but it blows up regardless. So it's going to be, so c goes to 5. That one was easy. Now this one's interesting. So this one only has one fixed point that's it has just one saddle. So it's, so if like x is 0, so it's probably this. It's probably 6. Because if y equals 0 and x equals 1, then it's at this fixed point, but it's going to run away. So I'm going to say that d goes to 6. All right, let's check that out. So this is 2.1. Are we in 2.2 right now? I think we are. All right, here we go. So A is 7, B is 8, C is 5, D is 6. Let's go. All right, 13. All right, we can get back on the board. I'm excited to get back on the board. Doing problems on a whiteboard just makes you feel so much better than everyone else, in my honest opinion. Oh wait, no, yeah, okay, all right, good. Okay, so what happens here, right? How do we figure this out? I mean, the first thing is we'll just do this. 4 minus 7, 3, 6, minus 2, 1. So this is our system. So let's just do this. Equals, so this is going to be, we're going to multiply this by 3, so we're going to get 12 minus 21 minus 6. Then we're going to multiply this by minus 4, so we're going to get minus 12 minus 24 minus 4. This would be 0 minus 45 minus 10. So then we have 45 y equals 10. Y equals 2/9. So we have 4x minus 14/9 is equal to minus 2. This is minus 18/9. So 4x equals minus 4/9. X equals minus 1/9. Right, so that has to be the only equilibrium point because this column is not a scalar multiple of this column.
How did you know? How did you record?
Mm-hmm.
The video you fixed on?
Okay. So that's a fixed point, but then what we want to know is the behavior. We want to get a geometric picture of this thing. So if we're at minus 1929, we're right here. We're at 0. But then if we, let's see. All right, let's just do 0. So f of 0, 0 is going to be 2 minus 1. So here we're going to be going this way. Oh, so we're going to be going kind of like this way. Okay, if we just so I guess a good question is how do you do affine linear? How can we do affine case like x dot x prime equal to 4x minus 7y plus 2y prime equal to 3x plus 6y minus 1. Okay, so we got the equilibrium points. Now you shift to the origin. Oh, okay. So you just take the yeah. You just take the linear part, you do the Okay, so you get these eigenvalues. Both have real part. Okay, so what it's gonna do is then, because they're both unstable. Oh, but see, that's a little bit harder. I mean, in the long run, they all go away, but what really happens is it starts to spiral around it. And how do we know if it's clockwise or counter? It's got to be a counterclockwise, but I don't know why. Just telling by the picture it's counterclockwise. To see which way trajectories spiral around the fixed point, you need to probe the vector field on either side of it. Okay, so yeah, it's a counterclockwise spiral away from the fixed point. All right. All right, 15. This is going to be hard because this one's not linear. The linear ones are nice, man. Linear differential equations and affine linear differential equations are a lot easier to analyze, I'll tell you that. So it's going to be going like that. Okay, so cos W equal to 0 has W equal to pi over 2 plus k pi, because, you know, this is a 0 and this is a 0. So for, k and c. Now, so that means that we also have so this is the fixed point, is pi over 2 plus k pi over 2 plus k pi. Because if you plug this in, this is 0. Then if you plug this into here and this into here, then it's 0. So you're going to have, oh wait, you're going to have, you're going to have these zeros along here. And you know what? I'm going to try something kind of fun. Let's I'm going to switch this to this. Hello? Test, 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 test. Now we got a real mic. But the thing is, I don't know if I like this. It's better for when I'm on the whiteboard, but worse for when I'm on the Can you hear me from over here? Maybe? I don't know. Probably a little low. Okay, but we're just doing problems, right? So okay, if we have can we always linearize? I think we might be able to, right? So we're gonna get okay, then we're just gonna plug in a point like 0, 0. I mean, if we just plug in a point like f of 0, 0, we're gonna get cos of 0, which is 1. So we're gonna get equal to 1, 1, and then we're gonna get 0. So along this axis, this thing is going this way. Okay. So how do you get like a good geometric picture? Maybe like okay, well, if we is it gonna be like this all the time? Because it's gonna be 0 here. Wait. Oh wait, I did this wrong. This isn't one of them. It's gonna be like this is not one of them. But we are going this way here, but that's not a fixed point. So these are all fixed points. But okay, if we find the eigen wait. If you have so this is the Jacobian. But so we should be able to just plug in for pi over 2, right? So then we get 0. So this is going to be pi over 2. So sine of pi over 2 is, so this is going to be minus 1. So then if we find the eigenvalues and the eigenvectors. So we're going to get minus lambda, minus 1. So we're going to get, the determinant is minus lambda plus lambda squared minus 1. What's the solution to that? I don't know. If you were to just plot z dot for different, so this is w and this is z. If you were to just take z equal to 0 for all cases, then you should get like a wave along this axis, right? And it now if you have w is equal to z, right? If which is this equation, if you're in uh if you're in, let's say, -1, 1, -1, -1. I can't get a good picture of this vector field. Honestly, anything with like nonlinear stuff in it, or even just like, I don't know, it's hard to understand. Let's do the Desmos thing. So this is going to be cos y, and this is going to be x minus y. Or no, minus x plus y. Yeah, wait, let's look at the eigenvals of 0, -1, -1, 1. So it is unstable. So there are two alternating types of equilibrium. When oh shit. That's the crazy thing, man. Is the cosines, you get this alternating behavior. We saw that in one dimension too. So we don't have a so these so along each of these, well you're not gonna really see it. Oh see, okay, so it flips. So see how this one's gonna go like this. That's really confusing. A non-zero sign divergence in the plane. Is this for a point? This is for a point, right? Wait, I thought the trace was the product. Oh, the trace is the sum of diagonal. No. Okay. Okay, so I don't know how they expect us to answer that question quickly because that one's crazy, right? Okay, problem 17. So if y is 0, x is so along this we're gonna have oh wait, I always mix that up. Alright, so this is gonna be pi over 2. This is gonna be okay, so then let's linearize. So our Jacobian is gonna be 0, 1. And then we pick pi over 2. This is going to be turned into for pi over 2, 0. It's going to be 0, 1, 1, 1. So then the stability at this point is going to be minus 1 minus 1. Isn't it the same? So wait, what are the solutions to this? All right, let's explain. I need a fast way to solve polynomials up on the board. Solve. Oops. Okay, so we do solve x squared minus x minus 1 for x. Oh. What does that look like? I love that websites do this. Like, why is their homepage like Google Docs? Why doesn't it always take you to the ad page? All right. So x squared minus x minus 1. Okay, so one of them is positive, so it's unstable. So along one direction it's stable, and on the other direction it's unstable. So, but how do you know? You have to then solve for the okay, so but then you have to do a bunch of algebra. This is brutal. let's see. Well, okay, let's just say we're at 0, 0. F of 0, 0. Let's do this. We're going to get 0 minus 1. All right, so we're going to decay down this way. So it's probably like this. So if we put in pi here, we would get 0 cos of pi is minus 1, so we'd get 1. So we're actually going to go up here. But then somehow this like goes out like this. So if y is anything, then x is just going to blow up. So something like that. All right, let's plot. Let's plot. What the heck does that vector field look like? So we have y minus cos x plus y. I must have done something wrong. If y is 0, then cos x has to be 0. Oh, okay. So I flipped it. So just rotate my graph. I think in this problem though they ask you to sketch the direction field so that you can describe it. So if we were to do that, these are just going to go off to infinity, I think. The farther you are away, but I don't know if they go to infinity. I can't tell. Because like, aren't they going to loop back around at some point? No, they don't. They don't. They go like this and they just go on a line. If you take these close ones, they just go like this. Okay. All right, number 19. Are we? Number 19. Number 19. All right. So what do we got here? We got, let's just say x prime equals y, y prime equals, now this is weird. So what this turns into is y prime, wait. Okay, so y prime is equal to minus 2y plus 3x plus x cubed. So then f of x, y is equal to y minus, this. So that's part A. Can you read that? Can anyone actually read that? Maybe I should do. All right. So the fixed points. So y needs to be 0, right? No matter what, y needs to be 0. So y equal to 0. That's the only thing. So then we're gonna get 3x plus x. Oh wait. So we're gonna get So then we have so these are the fixed points. Now the phase portrait. So okay, wait. Now they allow us to look at the direction field. So let's look at the direction field. So so this is good, and then we're just gonna do minus 2y plus 3x minus x cubed. Oh, whoa. Look at it. Holy frick, bro. But it does look like it, I can't tell if it, what it does. It's hard to say. I mean, yeah, it gets big, but like, it looks like it forms an ellipse. I wish they plotted a solution. Let's just ask ChatGPT. Wow, it actually writes its own runga kata. That's crazy because it knows that well, but it has SymPy. Doesn't SymPy have that's pretty nuts that it just writes a I mean it's literally like 5 lines of code. It's just funny, you know. Mm, it does seem like should we do a linearization? Maybe we'll do the linearization and see. Dude, this rules, man. It's so nice that you can just like oh wow, that's beautiful. Yeah, so okay, so we have to bro, we have to look at this. So we're gonna all right, so let's find the Jacobian. Why don't we just do it symbolically? I mean, I don't think we need to. Show me how you take jack symbolic jack. It's got to be like a dx one. Like you probably just use d. Why is it thinking so hard about this? Also, I didn't even find Jacobian matrix. Huh? Oops. Yeah, I don't even think this is a real thing. Oh, it is. Oh, it's a resource function. It's nice that you don't have to do that. Because for D, you have to do like, because dx of t, yeah, but because you need to do, um, I feel like that's what I did. Okay, so now what we want to do is j slash dot x2. What was our fixed point? Wait, but wasn't there another fixed point 0, 0? Okay, so let's do 0, 0 first. So x to 0. I wonder if you can do this. Can you do x, y? No, that's goofy as hell. Okay, so we get. Okay, so then clearly our. So wait, can we do eigenvalues of percent 7? Yeah, so that's what I thought. Oh, but you know what's weird about that? It's like I don't understand why. Like if you have 2003, why is it that the first eigenvalue is 3 and not 2? Kind of weird, right? Okay, wait, but we want to figure out the stability. So wait. Hold on. Didn't we just figure out the stability? Because we took the Jacobian at that point, and then we plugged in the fixed point, and they're both positive, so it's unstable, It's like unstable in both directions. Okay, but it looks like uh, it looks like that's a terrible plot. ChatGPT. Oh, ChatGPT. This These look stable no matter what. Also, this vector plot is like 1,000 times better than this. The only reason why I like this one is it's real time, but it's like maybe I should just. I mean, this is such a better plot. Like this other one just doesn't tell you anything. Wow, this is so good. Okay, so then oh, it returns them sorted. That kind of makes sense. Okay, so is that true? Yeah. Wait. What if we do? Is this right? Okay. That's Oh, that's so cool. Whether to use cubics or quartics or whatever. Oh, that's so cool, man. I love numerical linear algebra. Can I'm probably so quiet. I need to talk loud when I'm over here. What you know what I could do though? I feel like I could just. Oh, actually, I'm probably actually using PNP. Right? No, I'm using 500. Maybe I should just do this. Because look, I never use this. I'm just going to do this. I never really use that. It's so bad. But what I could do, this might sound super disorienting, but maybe I'm just gonna do this. Oh wait, you know what? I actually didn't. So this is gonna be 5 fine, and wait. Oh, because I have gain on this one. Let's properties. This is just gonna be test. Okay, so maybe it sounds like duplicated, but at least I'll have reasonable gain everywhere I'm at. Okay. So wait, so hold on. What was happening is we wanted to just redo this. So since they're all positive, now we want to do this. To what is it? It's going to be 0. No. It's going to be square root 3. Oh, 6. So they're both. Yeah, hell yeah. Wait. What? What? Wait, why did this not work? Minus square root of 3 should be. Wait, this isn't even the right. Wait, what? This isn't even the right thing. Dude, what is going on? That was terrible. Okay, so this is y. I can't believe it used that old example. That's pretty annoying. Minus 2y plus 3x minus x cubed. I can't believe that misled me for so long. There we go. Wait, okay, so actually this is a saddle, which actually that looks way more correct. This is clearly a saddle. Because we have this, and if we looked at the eigenvectors, we'd see that there is something that goes to this saddle. All right, so now we can look at this, but but the sign didn't. What? Sign of a complex number? Yeah, okay, so it's undefined. So what we have to do is we have to put in RE. Okay, so there we go. So it decays. It's stable. So no matter what, this thing is stable. It does twist, but it's stable. All right, I really like that example. I like the ones with complex eigenvalues. All right, 21. 21 I think we can do without the board. I remember doing this one. So it's basically like match these things. So so this C is the easiest because C is just going to be this one on the far left. Then this one with the lowest amplitude. Wait, hold on. So these are going to be those center ones. B is going to be this one that goes out and around. But we want to figure out, so if we're starting like here or something, y is 0. Y is 0 there too. But then where does y gets bigger on this one, right? So that means that this one's that one, and then this one is that one. Okay, 21's done. 23. This is going to be offset decaying sine and cosine, but they decay. This one, I think this one just looks like this. All right, cool. All right, I'm gonna end the stream. We're going to hop into 2.3, and then we're going to do 2.4, and then we're going to do 2.5, and we're going to be 6, 7, and 8, and then the review exercises. I'm going hard on differential equations this week, bruh.